Okay, so the last thing that we've got in our heat unit is going to be on heat transfer methods. You probably heard of all of at least these three before, and we're going to go over them real quick, make sure you have a good background in them, and we'll even tie in a little bit of the fluids unit when we talk about convection. So first up, we've got conduction. You'll notice I've got a fire here, I've got a pan with boiling water in it, and let's go from there. So conduction, this is the one you're probably most familiar with. Conduction is when you basically just touch it. So it takes place with direct contact and can happen in any state of matter. And basically what goes on in this one is fast-moving particles collide with slow-moving particles and transfer energy. And it continues until both substances have the same temperature. That's the one you're probably most used to. You touch something hot, you slowly get warmer. The next one we'll talk about is convection. And in this one, it happens only with fluids, so it happens within only fluids, where warmer, and because they're warmer, they're bouncing around, they're spread further out, so warmer, low density, low rho fluids rise, and cooler, higher density fluids fall. So the higher energy ones can move further away from the pole of gravity. They're less dense. The heavier stuff falls down, or the denser stuff's going to end up at the bottom. That's how convection works. You see in water where it does like that. If you've got a convection oven, it cycles the air through. And then finally, radiation. You can see waves coming off of there. This is where energy is transferred through a vacuum. Oops, that should be 2 U's. By way of electromagnetic radiation. And there you have it, the 3 methods of heat transfer. But now we're going to get into more specific cases where we can see how it will transfer with objects that have different, differing areas and the rate at which it can flow through them. On this last part, we're going to look at how heat flows between 2 objects with some type of thermal contact in the middle of them. And in this specific case, imagine we've got some object that's got a temperature. This one's going to be higher than that one. They're connected by some object that's allowing heat to flow between them. It has some area that's connecting them and some length that they're separated by. And what we're going to look at is how heat is going to flow across that. So how much energy per unit of time is going to flow. You may have heard of the unit of energy over time. It's watts. But we're going to look specifically at how this works. Our equation we get with this is that our heat flow rate is equal to K, which is a specific heat constant or a thermal conductivity constant. And it's going to be equal to, or multiplied by the area times your change in temperature, or the difference in temperature between the 2 sides divided by the area. So K is your thermal conductivity constant. That's going to be unique to every substance. Each one's going to have their own. And it's in terms of units of joules per seconds, meters, degrees Celsius, or you can also have it in terms of watts per meter Kelvin. Joules per second is watts, and degrees Celsius and Kelvin are both the same thing because it's a change in temperature. So on this problem, for instance, like let's say I had copper in here. The longer that I make it, the slower the rate of heat transfer is going to be because it's inversely proportional. The more thermally conductive I make something, the faster the temperatures are going to change between the sides because higher thermal conductivity constant, then more heat is going to be transferred. Same thing with area. Bigger area for heat to flow through, then the heat's going to go exchange faster because there's more spots where particles can contact with each other and energy can flow. And finally, the bigger the temperature difference, the faster that energy is going to flow. If I got particles that are moving significantly faster on this side than that side, when they contact, they're going to transfer that energy in and it's going to spread really quickly. As the temperatures begin to equalize, though, the rate at which heat transfers out slows down quite a bit.